Hi, this is Miss R, and we're going to talk about Lab 6.04, levers and work. Part 1, you need to watch a TED Ed video, The Mighty Mathematics of the Lever, right here, and answer these 5 questions. I think you can do that on your own. Here's what the TED video is going to look like. It's about Archimedes and his thoughts on levers. He said, if you give me a place to stand, I'll move the world, and you'll figure out exactly what that means and what he would need to move the world. For part 2 of the lab, we'll be using the PhySci simulation, and I'll show you where that is. Make sure in the PhySci simulation you have rulers turned on so you can see where you need to put the objects. So when you go to the website for the PhySci simulation, it'll be clicked on this intro, but you want to do Balancing Lab. So simply click on Balancing Lab and you're going to come to an environment like this, and make sure you click on rulers. And when you want to see if the object's actually going to balance, to remove these columns that are holding up this lever here, this kind of teeter-totter, you want to slide this over, and those will disappear, and then you can see if you put 2 different masses here, the teeter-totter will respond accordingly. So now that you're familiar with the simulation, we can start working on the lab challenges. Our first challenge is to place 10 kilograms at 1 meter to right of the pivot. So that's going to be right around in here. We'll look at the ruler and figure out where we would place the 5 kilogram mass in order to keep it from rotating. So we have 10 kilograms at 1 meter over here, and we've got to put 5 over here to see how we would keep that plank balanced. So I have these columns holding my meter up. I'm going to click rulers. I'm going to take 10 kilograms and put it at the 1 meter mark. And now I have to figure out where I would put 5 kilograms to balance it out. Let's start at 1 meter and just see what happens. Let's remove our supports. Oh, well, that's not in the right place. Let's move it a little bit farther away. That's better. Let's do that. Is that going to work out? Yep. And that makes sense because there's twice as much distance here, but for half as much force. So it all works out in the end. Twice as much distance. This is 2 meters and 5 kilograms, and this is 1 meter and 10 kilograms. So if you multiply the force, actually the force of gravity, which would be, we'd have to multiply 9.8 meters per second times the number of kilograms to get the newtons of force. But if you multiply this force times 1 and this force times 2, it all works out. They'll be even because the work being done on both sides of the levers, is always going to be equal. And that's an important thing to remember when you're studying simple machines. So we've just done number 6, where we put the 10 kilogram mass and tried to balance it with the 5 kilogram mass. So you know what you need to know to answer that question. Now let's place the 20 kilogram mass at 2 meters to the right of the pivot, so right about over here. And where should you place additional masses to achieve static equilibrium? Include the amount of mass and location. So let's go experiment. We've got 20 kilograms at 2 meters, and we have to balance that out. So I'll point out in the simulation an important thing. This orange button here in the lower right-hand corner is a reset button. So if you want to just kind of clean up everything you did from the previous question, you can hit reset, but then remember to hit rulers again. So we have to put 20 kilograms at 2 meters on the right side, and we have to think of what's going to balance that. Well, we could use 40 kilometers, or 40 kilograms, sorry, at 1 meter. Oh, they won't stack on top of each other. Well, that's not going to help. How about we put 20, that's too easy. Let's put 20 kilograms here and 20 kilograms here. That's going to work out to about 5 kilograms. And let's put 5 kilograms here and see if that works out. Oh, we're going to have to move our 5 kilograms out. Not quite enough. Let's move them out here. Oh, there we go. So I could have just put 20 kilograms out here and that would have been interesting, but it was more fun to kind of do something a little bit different. We put 20 kilograms at 1 meter, which only counts half as much because it only has twice half as much distance as this 20 kilograms. This 20 kilograms only has a quarter of the distance, so it only counts as a quarter of what this is. And this 5 kilograms has the same distance. So for it to all add up equally, we needed to put a number of different weights at a number of different distances. You could, of course, though, also just, oops, I reset it, so I need to put rulers on. You could have just done this too, but this is kind of boring. Put the same weight at the same distance. Now that you've done question 7, let's talk about question 8. Place the 20 kilogram mass at 2 meters to the right of the pivot. Make sure the plank is in static equilibrium using only 5 kilogram masses. Where did you put the 5 kilogram masses? Well, let's go figure it out. Okay, so we need to put a 20 kilogram mass at 2 meters, and then we need to try to balance it out with 5 kilogram masses. And since you can't stack them, it'd be nice if you could just put them all on top of each other, but that doesn't work. So let's just try doing this. Let's put them as close together as we can. And from some perspective, it seems like 20 kilograms over here should balance 20 kilograms over here, but let's see if that happens. Nope, it's not far enough out. The distance between this 20 kilograms and this 20 kilograms is not the same, so we're actually going to have to keep adding bricks over here to make things balance out. Let's add it right here and see if that works. Oh, check that out. We figured it out. It actually takes 5, 10, 15, 20, 25, 30 kilograms over here to balance the 20 kilograms over here because the distance is different. So for number 8, we just did that. You saw that we needed 20 kilograms in lots of different places over here to balance the 20 kilogram mass over at 2 meters. So we saw that distance does make a big difference. So now you can answer number 9. And in number 10, you can answer what role the mass plays in balancing the plank. What would you need to balance the plank in a weightless environment where gravity wasn't pulling on the masses? I'll let you think about that one. So now we need to do some calculations. We can calculate the force by multiplying the mass of the bricks by the acceleration due to gravity here on Earth. So in order to find the force of gravity here on Earth, we multiply the mass times the 9.8 meters per second squared. So you can see that they've done an example here. If they put the mass, a 20 kilogram mass on the left at 0.5 meters, they're getting the force from the mass, from the force of gravity pulling on that particular mass, times the distance here, is going to equal the mass times the distance here. And here you're not going to know the distances, so you're trying to solve for this distance. Because work here equals force times the distance. So we have the force here, this calculation, the mass times the acceleration due to gravity is the force. I'll highlight that for you. And here is the force over here. This is mass times acceleration due to gravity. So that force is different for both sides because the masses are different. So in order to do the same amount of work on both sides, work is calculated, remember, force times distance, they need to have different distances. So over here, it's 0.5. Here we have to solve for it, and they basically solved for x here. Let's actually do a problem here, and it might make more sense. So we're going to start by multiplying our 20 kilograms over here times 9.8 meters per second. That's our force on the left, times the distance, times 1, that's 1 meter, is going to equal, we know the kilograms here are 10, and we know the acceleration due to gravity is the same, 9.8 meters per second here on Earth. We don't know the distance. So we can solve this by using a calculator, and I'll get out my calculator here in just a moment. So when I take my handy dandy calculator here and I multiply 20 times 9.8, I get 196 times 1. And when I multiply 10 times 9.8, I get 98 times x. So now all we have to do is divide both sides by 98 to solve for x. I'll show you how to do that. So now if we divide both sides by 98, we can cancel out this 98. We can do, we'll just make that 1 because 98 over 98 is really 1. Oops. So now we basically have 1x equals 196 times 1 divided by 98. Well, you can do that on your calculator. You can take 196 and divide it by 98. Let's do it right now together. 196 divided by 98 equals 2. So the answer is 2 equals x. Now, does that answer make sense? I'm going to be a good student here and put my answer in a color other than black, because remember, you lose 10% if you don't do that. Does that make sense that a 10 kilogram mass would have to be twice as far away as a 20 kilogram mass? Let's go check our answer in the simulation. So if we take a 20 kilogram mass and we put it at 1 meter, let's put it at 1 meter over here because that's how it goes in the simulation. And then we take a 10 kilogram mass, and we put it over here, is it going to balance? And it balances perfectly. So we did our math correctly. So I'm going to let you fill out the rest of that table and you can check your answers in the simulation. You can just kind of guess and check in the simulation as well if the math freaks you out. So I color-coded things here to make your job a little bit easier. I put all the distances here in orange, so you know that when you go into the formula here, the orange numbers are distances. So you take the mass times 9.8, and that's the force here. Force is colored blue up here to help you remember. And same thing over here. You take the mass and multiply by 9.8 to get the force. We'll highlight that in just to make it super clear that the blue highlighting is force. And then the distance is 1 here. It's 0.5 here. So the distances, remember, are orange. And it's orange up in the formula here too. So it's force. It's blue times orange equals work. So here you'd have to take blue and multiply it times 9.8 meters per second to get the force. So 80, put that in parentheses. I'll start the next one for you. Times 9.8 meters per second. That's the force. The distance is 0.25, and that's going to be equal, so now we have force in blue, and distance in orange, and we have that has to equal force times distance, which is work. Work on one side has to equal work on the other side, so we have to multiply 20, which is the mass on the other side, times 9.8, that's acceleration due to gravity here on Earth. And then we don't know, so we have to put an x here. Let's put it times x, so it's very clear that that's the distance. So this is the force in the work formula. Remember, work is force times distance. And then the x here is the unknown, so you have to solve for that unknown. And I showed you how to do that by rearranging the formula up here. So you should be able to do those on your own. If you want, you can always check them in the simulation, but try using the math if you can. For number 11, you're also going to have to use mass. Remember that 10 kilograms is going to be your mass. You're going to have to multiply that by 9.8 meters per second per second. 1 meter is your distance. So remember, force times distance, this times 9.8 meters per second is your force times the distance will have to equal the force, this mass times 9.8 meters per second, the acceleration due to gravity, times the unknown distance. So this is B where, we'll call that x. So we don't know where that distance is. So we'll call it x, so you know that you're going to solve for the distance just like you did above. So you know enough to solve problem 11 now. So for question 12, you need to look back to question 11 and draw the forces acting on the plank. Draw the two masses, the gravity pulling on the two masses are the forces. And so here is one of the forces here. This is, I called this the 10 kilograms at 1 meter. And you're going to have to figure out how to draw the second vector. I just inserted these arrows using the insert menu, insert object menu at the top of my Word. You can do it other Google Docs and OpenOffice will have similar features you can use to insert an arrow, and you can figure out how to do the size and spacing of the arrows based on your answer to number 11 up here, where you used math to figure out the distance for this 15 kilogram mass. So number 13, how many forces did you draw? And would this object be in equilibrium? Explain why or why not. So I will let you do that, do some thinking. Thinking's good for your brain. Now let's imagine a different setup here, where we have just one side of a lever. What would this scale read? Now remember, scales measure force, not mass. So it's measuring how hard you're pulling up. If the plank is in static equilibrium, that means it's just standing there. It's not moving up or down. It's just steady. The 15 kilogram mass is located 3 meters away from the pivot. You're going to show your work. Remember Newton's third law. For every action, there's an equal and opposite reaction. Okay, so before you completely freak out because this question looks really hard, let's consider a couple things. That the work done by the scale has to be the same as the work done by the mass plank system here. So if we want to figure out the work done by the 15 kilogram mass at 3 meters, we have to take 15 kilograms times 9.8 meters per second, that's gravity, acceleration due to gravity, times the distance. Remember, the distance is 3 meters right here. And that will be the total work done by this. Now we know that the scale has a force, it's pulling up, and it's at a different distance. So we have to figure out the force that the scale is reading, the upward force, to overcome the work done by to balance out the work done by the 15 kilogram mass at 3 meters. So here's the work done by the 15 kilogram mass times 9.8 meters per second to get the force times the distance. We don't know the force on the scale, but we can figure it out. And we know it's at 4 meters because we know if this is 1, 2, 3, the scale is at 4 meters. So the distance for the scale system is 4. So now all we have to do is solve for F there. So if we multiply 15 times 9.8 times 3, let's do that on my calculator really quickly. So when I multiplied 15 times 9.8 times 3 to get the work done by the 15 kilogram mass at 3 meters, I got 441. So the work done by one system, it needs to be equal to the work done by the spring scale at 4 meters. So all we have to do, we basically now have 441 is equal to F divided by, or F times 4. Let's scoot this up together so they're a little bit closer. Now we just need to divide both sides by 4. So divide this side by 4, oops. Oops. Let's see here. There we go. And divide this side by 4. These 4s will cancel out, and we get just F equals 441 divided by 4. You can do that on your calculator. So what would be your answer to the scenario in the problem above, which is actually B14, if I told you the mass of the plank was 5 kilograms? So now you've got the mass of the plank adding to what you need to pull up with the scale. So instead of just the force of the scale, so let's look at the math. So in addition to the force of provided by the scale on the left hand side at 4 meters, you're going to have to add the force of the plank here, which is the 5 kilograms times 9.8 meters per second. But you can still, you know this because you've solved for it up here, so you know what this is, because you solve for it in number 14. And you can do this on your calculator, so it's not that hard. See? Calm down. It's just fine. Okay, now we need to solve for an unknown. You will determine the masses of mystery packages based on known objects and distances. So instead of finding the distance this time, you're going to have to find the mass of the mystery package. And you're going to have to use math for this one. You can't just guess and check in the simulation. And it works a lot like last time. You're going to have the force, which is the kilograms times 9.8 meters per second, times the distance, but you're not going to know this second mass. You're going to be solving for this x, the mass of this mystery package, which in this case turns out to be 20. So let's see where the mystery packages are here. I reset the simulation, so I'll put the rulers back on. And then we can go and look at different objects here, well, or people. And here are the mystery packages we're looking for. So for the second example here, we're looking for a mass of 30 kilograms at 1 meter balanced against a mystery package at 2 meters. Mystery package C at 2 meters. So 30 at 1 and C at 2. So let's go and put a 30 kilogram mass right here. And let's put package C at 2 meters and see if they balance. All right. So they do. Now let's go do some math. So we saw that our 30 kilogram package, that's the mass, and we always have to multiply that times the acceleration due to gravity here on Earth, which is 9.8 meters per second, and that is our force, and we need to multiply that times the distance in this case, which is 1 on the left-hand side, and that's going to be equal to mystery package C. Let's just call that the mass. We're solving for C to find the, whoops, that thinks it's copyright. We would have to multiply that times 9.8 at a distance of 2 meters. So we need to do a little math over here. 30 times 9.8 is 294. That's my force times my distance. And then I've got C, what we're solving for, times 98 times 9.8 times 2. So let's multiply 9.8 times 2. And if some of you are going, hey, couldn't we eliminate 9.8 on both sides? Because using algebra? Yes, you could. Now we've got 294 equals C times 19.6. Now we can just divide both sides by 19.6 to get C by itself. So we'll decide the bulb. You don't want that underlined. So divide one side by 19.6. Divide both these sides by 19.6. This, of course, these two will cancel out. This 19.6 cancels this 19.6. And the answer is 294 divided by 19.6. I'm going to let you do that on your calculator. So 294 divided by 19.6. And now you have the general way that you put in numbers into the formula to solve for this unknown. So to solve the next one, remember you just multiply 30 times 9.8 meters per second times the distance, and then d, your unknown, times 9.8 meters per second times the distance, and then solve for d, just like we did here with c. And when we divided both sides, the 19.6 canceled out, and then that was your answer. So just to have a little bit more fun, in part 5, we're going to put 2 objects on one side and 1 object on the other side and solve. So we're going to use the mass times 9.8 times the distance. That's the work of one object, plus the work of the second object. Use that mass times 9.8 meters per second to get force times the distance. So we have work of the first object plus work of the second object is going to equal work of the third object, and we need to know what the distance is for that third object. So let's do the first one together. So we're going to have to find the force. That's 20 kilograms times 9.8 meters per second plus the times the distance. That's force of the first object. We're going to add that to the force of the second object on that same left side. So that's 60 kilograms times 9.8 meters per second times the distance, which here is 2 meters. We'll put in a time symbol just to make it perfectly clear. That's times, force times the distance. And that's going to equal to the work done on the other side, which is 80 kilograms times 9.8 meters per second. But we don't know the distance. So it's times, let's call it capital D. And then we're going to solve for capital D. So all we do is we need to multiply all of these numbers together, multiply all of these numbers together, and multiply these numbers together. So I'm going to do that on my calculator. Okay, let's talk about the calculations. So this 196 number is the work done by this force, 20 times 9.8 times 1 on my calculator. These multiplied times each other is the work done by this first object over here. We just put 9.8 in there to figure out the force on that first mass. That's the work done by the first object. The work done by the second object here in green is the mass times 9.8 meters per second, that's the force, times the distance. So if you multiply 60 times 9.8 times 2 on your calculator, you'll get 1,176. If you multiply the force for the first one, for the right side over here, the force times the mass times the acceleration due to gravity to get the force, so that's 80 times 9.8, you get 784, and you still have to figure out the distance, d here. So you have to add these two numbers and divide by 784 to solve for d. So don't panic, I'll explain what we did. We just took these two numbers, the work from the left side, and added them up. 196 plus 1176 is 1372. And then we have to solve for d here. So 1372 equals 784 times d, just like it was up here. And then I just divided both sides by 784, cancels out here, and our answer is just 1,372 divided by 784 is going to equal the distance d here, right here. And so that's how you figure out the answer to these problems. You need to figure out the work from the first object, add it to the work from the second object, figure out the force from the object on the right, and then solve for the distance. You're smart people, you can do that. So now the wrap up is just how do levers make life easier? Think about ways you use levers in your everyday life. Do you use a can opener, a pair of scissors? Are there other tools? Have you ever used a screwdriver to pry something open? Think about things you use in your everyday life that are levers that help you. And then write a couple sentences using these 6 words. Thanks so much, everybody. I hope to see your labs handed into the assignments areas soon. Bye-bye. This is Miss R signing off on Lab 604.